Okay, I think it's time to start. Thanks for the well wishes, everybody. I am fine, and here we are back again. I think we all just had to have our turn to be sick. I'm sorry if that's your turn right now. We will all hopefully get through that. Happy Wednesday. That's good. Happy Wednesday, everybody. Oh, mini quiz time. So I made you a mini quiz. I tried to make it pretty straightforward because I know you were working on those first 5 homework problems without a kickoff lecture, but what they're on was pretty simple, I hope. So I may or may not answer a question if you ask it to me. Probably not. Oh, computers away, phones away, watches away for the mini quiz, please. Remember that you can speak to anyone. Talk to anyone at your table, anyone at the next table, but phones away there in the back. Computers away, all that. And good luck. Oh, and I'm going to try to get this thing to work. Is there extras? Are there extras here? All right. Sorry, guys. Anyone need them? I'm sorry. Remember, you can ask a table next to you if you want to double check.
She was like talking about how like what inspired her.
I plugged something in.
All right, one more minute, maybe half a minute. Get your answers down. Sometimes I have them in my wallet. Let me just look. So I have a son, and this is sometimes necessary, but also it means sometimes they are used up. Oh. I gotta remember to put one back. All right, hand those up to the front, please. Thank you. Thank you. Any more? Any more? Is that one right there or? Okay. Okay. All right. So what do we think the answer is? D. Oh, your mask fell off. Who thinks D? Okay, that seems pretty good. Okay, so people think D. Look what I figured out how to do. I figured out how to use this thing finally. That took a while. It's only what, week 6, right? I just asked somebody, how do you turn this on? Because it doesn't go on. Okay, so fine, it is now on. Why D? Plug -1 in. Now, okay, so that's true, but I want to draw you a picture too. So what's going on here is you've got the function that's 6x when x is less than -1 and 2x minus 4 when x is greater than or equal to 1. And you're right, when you put 1 into this thing here, you get 6 times -1, which is -6. Sorry, -1. And when you put -1 into here, you get 2 times -1 minus 4, which is -6. And if you like to think graphically, what's happening here is you've got the function 6x, which kind of looks like this. It's a line of slope 6. I know that's not really steep enough to be 6, but just pretend my scale is what it needs to be. And this point right here, I guess where it's open, is -6. And to the left, the function is going to do that. And then the other function is 2x minus 4. And that's a function of slope 2, different slope, less slope, goes through -4 as a y-intercept. So there's kind of a corner here. My hole is not very artful, but that's just a hole. And the question is, what height would we have to fill in the function with in order to make this function continuous and it's that missing point? Yeah.
So I have two questions. So first, does it ever happen that you plug in the value and then like it's not true because of the other part?
Yeah.
Okay.
Yeah. Because like if this second one, if the height had been like 3 or something, then this line would be up here and there would be no value. Then the answer would be A. There'd be no value that I could put in to sort of repair this situation. But this is called a removable discontinuity because we can remove it or we can fix it just with 1 point, putting 1 point in the hole. Yeah.
My other question is just like there's a question on the homework that's does like this, except for it's not that kind of function. It's like a fraction, but it has like two like the x squared minus the factoring ones.
Yeah.
How would you solve that?
Those as you do more of these, you'll find that like you can identify when there's a hole, like if factors match, or if there's a 0 in the denominator but not the numerator. And we'll go over that, I think, start going over that in this section, and that'll keep coming back. Yeah. But you can also, I mean, technically what we just did, well, hold on, let me get your question first. I did, and I did something there that is sort of like the new thing from this chapter. So I'm actually glad you asked that. That's what I was about to say. So if I look at the limit as x goes to -1 from the left of the function, like what is the function approaching as I come in from the negative side? That is the limit as x goes to 1 from the left of the first piece, oh, sorry, -1 from the left of the first piece, because the first piece is the one that's on the left. And then this part here, this is the new part that we can just plug in to get the answer. So now, those of you that have done the reading and are ready to answer this question, does anybody want to take a stab at why this is allowed? Why did I compute the limit this way? Can I just plug in to calculate limits? Yes, yes, and no. Okay, yes. Why yes, though? Well, there's a magic word here about this function here, 6x. This is an extremely nice function. What kind of function is it? It's linear, right? But it also has a nice property. And that property is the topic of what we're doing today. What is the property that this function has that is so nice? Begins with C. What's that? but, oh, close. It begins with CO. CO, continuous. Yeah, continuous. So this function is continuous, which literally means that you can do the limit by plugging in. So that's what we're going to see today is that nice functions are continuous and you can do the limits by plugging in. If you have a piecewise function, you're going to have to come from both sides. Now this one you could do just by drawing a graph, but a harder one, you might actually have to calculate the limit from the left and a limit from the right. For real. You didn't have to write this on your quiz, obviously, for this one, but that's what's going on. Other questions about this before I start? Okay. Okay, great. That's done. Oh, I have some things to hand back to you. Oh, now, how would I now make this go away? How do I make it go away? That's a great question. Yeah, let's exit out. Woo. Okay, there we go. Technology. Okay, great. So I'll turn this back on in case anyone has any questions. That's why you got your phone out in the beginning. So if you have a question during class, feel free to put it here. I copied this over from what we would have done on Monday. I'm sorry that I could not be here on Monday. Did everything go okay with the quiz? Okay, Dr. Brown, was she nice to you? Terrible. She's very nice. Yeah. Okay, so this kickoff lecture didn't happen because I wasn't here. So it's actually about to happen right now. Okay, so there isn't actually that much to do this week. It's not like last week, which was a bear. So I'm just going to push that into here, and then we should be all caught up and everything will be great. You've already started your homework, which is great. The rest of the week is very straightforward. Next week is week 7, and I think I'm going to open up the retake qualifiers in week 7. So you'll have a couple weeks to like decide what you're going to retake and start qualifying for those retakes before we get there in week 9. Okay, so this is the last week where we're not going to be simultaneously talking about retakes, although I just talked about retakes, so I guess technically we are talking about them. I also have some papers to hand back to you because I was very sick on Friday when I normally would hand these back. Sorry. So I am going to hand them back right now. These are your quiz 4s, not the ones you just took on Monday, but the ones from the last week that normally would have been handed out on Friday. And Jada Marie, are you here? Because I have a paper for you, an old paper. Okay, so usual drill. I think I'll call this the projector instead of the door. So projector side, middle, or, ooh, that's cool. Or what's this, the podium? My brain got stupider when I was sick. Did you notice that? Just getting there. Okay, Matt, podium. Come on, this is the right section, right? Okay, Andrew, middle. Still the right section? Okay, good. Hayden, podium. John, projector. Gavin, middle. Annabelle in the projector side. Elizabeth, middle. Is Hayden not here yet? Okay. Rashna, podium. Lauren, middle. Taylor, this thing, projector. Patrick, projector. Jack, middle. Brandon, podium. Tyler, middle. James, projector. Tanner, middle. Adam, projector. Mira, middle. Do we not have Brandon yet? Lindsay, podium. Ethan, oops, Lindsay, podium. Ethan, projector. Nick, podium. Jesse, you're sitting right in front of me, I know. Do we not have Mira? Okay, Jordan, middle. Jeffrey, projector. No, Nick. All right. Landon, podium. Will, middle. Brooke, projector. Hannah, podium. We're almost done. No Hannah? Hannah? Oh, we don't have Hannah. Emily, middle. No Brooke yet. Sydney, projector. Caitlin, podium. John, middle. Allie, podium. Okay, no John Foss right now? Okay. Okay, that was week 4. Week 5, you'll get back on Friday. Okay, so I might have to talk a little quieter than usual today, just because I'm still like recovering, but I'm fine, so I'm not going to make anybody sick anymore. Here's this thing about continuity that we just talked about. You probably saw continuity in high school, but you probably defined it a different way, like with words, like with a sentence. Does anyone know what I'm talking about? Function is continuous if what? You can draw it without picking up your pen, right? You can draw the function without picking up your pen, that's continuous. That's mostly true. It's got some white lies in it. We'll see that as we go on. But it basically has the right idea, because if you're drawing with your pen, then you're saying that everywhere that your pen is headed to, it actually ends up there. And then it picks up from exactly that point and continues, right? So if you go from either direction, where the function is headed is actually its actual value. And look what I just said, where the function is headed is its actual value. It literally means that the limit is the value. Okay. Now, in general, the limit is not the value. Okay. Because otherwise, we would not have a whole chapter on limits, right? We already knew how to plug stuff into stuff, right? We didn't need a whole chapter on limits to do that. So in general, that's not true. But if the function is nice, then you can do that. And if you can do that, we say the function is nice. So for example, this function is continuous, and the limit as x goes to 1 is 1. It's the same as the value of the function. But here, the limit is different from the left and the right, and only one of those is equal to the value of the function. And here, the limit exists and is equal to 1, but the value of the function is different. And here, the limit exists and is equal to 1, but there is no value. Okay, so those last 3 are examples of discontinuities. A jump discontinuity, and then 2 more removable discontinuities like we saw in the quiz. You can be left continuous, like this function here is not left continuous because coming from the left where it's approaching is not equal to its value, but coming from the right where it's approaching is equal to its value. So this one's actually right continuous, but it's not two-sided continuous. And then there's another complicated issue about being continuous on an interval. I'll talk to you about that in a minute in a specific example. We might want to describe all the places where a function is continuous at once, and I'll show you that in an example in a minute. But this is your new definition of continuity, and this is really important. Like, this is more important than you can draw it without picking up your pencil, because you're going to need to be able to calculate limits and determine continuity from that. Discontinuity is the flip side. Discontinuity is when you are not continuous. We already saw there's this thing called a removable discontinuity, which means you could just change one value. There's a jump discontinuity, which means your function's sort of like broken, like an earthquake happened, right? And now there's a separation, but it's a finite separation. Or this one is very bad. This one is called an infinite discontinuity. Like, you can't fix this by shifting the function a finite amount. And you can't fix it by plugging a hole. There's an extraordinarily bad sort of divide by zero level thing that happened right there. Okay. Okay, so let's do an example. Clearly, this function is discontinuous at which 2 points? X equals -1 and x equals 1. And what kind of discontinuity does it have here? So this one's removable because I could just remove the discontinuity by moving 1 point. That's the least bad. Here's a tricky one though. What kind of discontinuity is here? Yeah, it does kind of feel like it's jumpy on one side and infinite on the other side, but I'm just going to say it's infinite. I mean, it can't be fixed. Even though both sides don't go to infinity, something infinite is happening there. So here's what's actually happening in terms of limits. At x equals -1, what we just said is there's a removable discontinuity. That was kind of easy just to talk about it out loud and point at the picture. Here's the new part, the hard part. Now you have to understand what that means is that the limit of the function is 2 up here, but the value of the function is -1 down here. And those are not the same. So the function is discontinuous at -1. Okay, and the type of discontinuity is removable because both these things exist, but they're not the same. On the second point, at x equals 1, the limit as x goes to 1 from the right is -infinity. I don't even need to say anything else. I could talk about the limit of x goes to -1 of 1 from the left. I could talk about how the value doesn't exist, but it kind of doesn't matter. As soon as infinity is in one of the limits, boom, you have an infinite discontinuity. Something terrible is happening here. That's enough. And then this is the part I was talking about with continuity on an interval. You can describe where the function is continuous using interval notation. Like everywhere up to -1, it's fine. But it's not fine at -1. So look, I have -infinity to -1, but I don't include the -1. Okay. And then in the middle here, it's fine, right? But it's not fine heading up this way. Is it fine heading this way? It actually is. So notice what happened here. That became square. Okay, because it actually is left continuous as I get to there. And then everything after 1, but not including 1 is fine. This is one of the only times that we will not use a union to describe these intervals. Because if we did use a union, we would lose this piece of information right here. It would look like it was continuous from -1 to infinity, which doesn't work. And I know that WebAssign has something weird about how it makes you enter this. There's definitely going to be a question about on Piazza about one of these homework problems and how WebAssign wants you to answer an answer like this. But we'll get to that later. For now, does anyone have any questions about continuity, discontinuity, and being continuous on an interval? Yeah.
So
Yeah. If it's, yeah, that's a good question. So the question is at the removable ones, do we always use the open bracket? And yes, because there's this hole here. So a removable one will always involve a hole, and the continuity will always end not quite at that hole. Okay, that's a good question. Other questions about this? Okay. Really, we're just learning this terminology, right? So we've got the terminology, what it means with the graph, and then we've got the sort of algebraic way of writing it down in terms of limits. That third part's the hard part, okay? If you've had calculus before, you might start tuning out because you know what discontinuities are, but you might not have thought about them this way, and that's what's actually going to be important in this class. Okay, so here is the really cool thing. Let me go back just for a second, just to this, about this thing with the arrow. If your function is continuous, then you can actually compute a limit just by plugging in. That's actually pretty amazing. So that means that the only limits that are going to be tricky for us to calculate are ones where something weird is happening, or we're not sure what's happening yet. But if we plug in and we get a nice number, then everything is fine. So I want you to just take a minute to your desk. I don't have a paper to hand out for this one because it's kind of short. But with your table, can you try to figure out what has to go in these blanks? Now, before you do that, I want to say that there are certain functions that are clearly continuous. Linear functions, their graphs are lines. They are continuous. So the limit of a linear function or a constant function or the identity function, all of those things, that limit is just going to be equal to the value. And less obviously, every power function is continuous. 3x squared, 7x to the 18th, everywhere they're defined, they're continuous. So at your table, see if you can figure out these things. And I want you to try to figure out why we don't know the answer to the pink one yet.
The last green one is.
All right, you guys ready to see the answers?
Yeah.
All right. So here's the answers. The number 6 as x goes to 2, well, 6 is just the function that's constantly 6 all the time. That's continuous. When we plug 2 to it, its answer is 6. I mean, the answer is 6 all the time. Okay, so that's 6. As x goes to 8, again, it's still 6, right? If I plug in 8, the height is also 6. That's constantly 6 all the time. How about this one? As x goes to 8, what does x approach? 8. Yeah, that's not rocket science. Now, we could prove with deltas and epsilons that this function is continuous, but I'm just going to lean on the fact that I know the graphs are lines. That's clearly continuous. So here's another line, 3x plus 1. So as I approach 1, what does the function 3x plus 1 approach? Why is it 4? Plug in 1 and I get 4. So because the limit and the value are the same, because the function is continuous, I know the limit and the value are the same. So I know, here's how the logic goes. I know the function is continuous. Therefore, I know the limit and the value are the same. Therefore, I calculate the value, and that is what the limit is. Okay, that's the logic. Same thing here. This is a power function. That's much more challenging to show that power functions are continuous where they're defined, but you can look in the book if you're curious. There's a proof in there. It's got deltas and epsilons in it. You can look just for fun. But we know the power function is continuous everywhere it's defined. We know that power function is defined at x equals 2. So we know that the limit and the value are the same at x equals 2. We know the value is 3 times 2 squared, which is 12, and therefore the limit is also 12. Okay, but all of that happened because I knew that I had continuity for that function. What goes wrong with the pink one? Why don't I know? I'm going to know it on the next slide, but why don't I know it on this slide? Do we know that a sum of power functions is continuous yet? No, technically no. I mean, we know that power functions are and linear functions are, but guess what? Here, now we know. So there's this rule that says if you have two functions that are continuous and you add them up, they're continuous too. Now, to be fair, that's not actually what it said, what I just pointed at it. What I pointed at said that the limit of the sum is the sum of limits. But a consequence of that will be that if you have two continuous functions and you add them up, and they're continuous at the same point, then their sum is also continuous at the same point. That's kind of a corollary of this. These rules look complicated, and you do need to know that they exist and what their names are, but they do sort of exactly what you would hope. Like if you want to take the limit of a product, you can take the limit of each piece and multiply together. It's exactly what you would hope would happen. If you want to take a limit of a quotient, you can take the limit of the top and the limit at the bottom and divide. Limits are super well behaved this way. In fact, even if you want to take the limit of a composition, you can just take the limit of the inside first and then take f of that. It's exactly, you'll see when you calculate, you use these all the time, you will. This one at the top says, if I want to take the limit of a constant times a function, I can effectively pull the constant out. Take the limit of the function and then multiply by the constant. These things would be very natural because nothing bad happens. Everything that happens here is what you would want to have happen. So here's an example. The limit as x goes to 3 of this sum, by the sum rule, that's equal to the limit of this thing plus the limit of this thing. Well, both of these things are continuous, so their limits are their values. So I can just plug in and I get 3 squared plus 3 cubed, which is 9 plus 27, which is 36. Now I put this little picture here, over here. That's from your book. It basically says that given any epsilon, we can choose a delta to get everything bounded in the right way in the sum. We don't need to worry about those proofs, but I just want to let you know that those are out there. If you're interested in like the theoretical underpinnings of why these rules work, you actually have most of the tools to prove these rules. We did skip section, what chapter in 1.3, because that was delta epsilon proofs. That wasn't really necessary for this course. This is kind of related to that section that we skipped. Okay, this is great. What I'm telling you is that we know how to calculate a ton of limits now, but things can still go wrong. So this is the good news. All algebraic functions are continuous on their domains. This is called the if you plug in and nothing bad happens, then the limit is the value rule. I just made, that's a terrible name for it, but that's what it means. If you plug in to a limit and you get a number, that's your answer. Okay, that's what that means. As long, well, piecewise function might be different. I was just thinking, if you plug in from one side, it's not always the same as from the other side. But in normal circumstances, if you plug in and get a number, you had an algebraic function to start with, like something over something with powers and roots or something like that, simple function, then the limit is the value. But sometimes you plug in and something bad happens, like this example here. If I plug in, don't even look at that stuff over there, just look right here. If I plug in x equals 1, what do I get on the top? And what do I get on the bottom? 0 over 0. I cannot even express to you how bad that is. It's very bad. I mean, you guys, 1 over 0 is bad, but this is like way worse bad. Like we don't even know what it is. The answer could be infinity. It could be 0, it could be pi, it could be 4. In this case, it turns out to be 2. Okay, we don't even know. So it's worse than something bad happening like an asymptote. It's something called an indeterminate limit, which we'll be talking about a lot in the next couple of weeks. It means we literally do not know what is going to happen at that point. 0 over 0. Literally anything could happen. World explodes, cats and dogs living together, or someone gives you a piece of pie. I mean, like anything. Okay. So what do? This is one solution for calculating a limit where something bad happens. So we plugged in, something bad happens. The cancellation theorem says if you can cancel, then the value of the limit before the cancellation is equal to the value of the limit after the cancellation. Okay. Even though this thing isn't defined at 1, that thing is defined at 1. And the cancellation theorem says those two limits are going to be the same. You can always cancel, and it won't change the value of your limit. So I can cancel. Notice this cancels out exactly the 0 and the 0 that were causing us problems. So now they are gone. And we're left with limit as x goes to 1 of x plus 1. This is a linear function, hence continuous. Hence, I can plug in to get the value. When I plug in, I get 2. That's the answer to it. So in answer to, there was a question over here at the beginning about what happens when there's a function that's a fraction and it has factors in it and stuff. That's exactly what just happened here. And this common factor here ends up putting a hole in the graph. So if I were to graph this function, it's actually really cool. This function x squared minus 1 over x minus 1, that seems like it should have like a complicated graph with asymptotes and stuff. But really, that function is the function x plus 1 everywhere except for 1. So here's x plus 1. And all I have to do is that. And this graph that's this function. That's pretty cool, I think. But any common factor just ends up poking holes in your graph. So we can poke holes in graphs, without doing a piecewise function. Okay, this is only the beginning of the terrible things that will happen to us with limits. Okay, like there are lots of ways that we can plug in and something will go wrong. And this is just the beginning of that. And it's related to the domain of the function, the behavior of the function, asymptotes and holes of the function, whether it's a piecewise function. And even in 232, we'll be doing this again, but with more complicated functions, trig functions, exponential functions, logarithmic functions. Does anyone want to ask about this cancellation theorem? All right. I think that this week, the only things that happen to you are you either plug in and nothing goes wrong, or you plug in and you have to cancel something. I believe those are the only two things that will happen on your limits this week. Next week, the gloves come off, okay? But this week, we're just getting our mind around continuity. And I have a paper for you about this one. So here is a paper with 4 limits on it that you can work out with your table. And this is this is the first two. I want you to try to solve the first 2 limits on the paper. I know they're not quite to the back of the room yet. I'll walk around and answer anything you need. Yes. As long as it's not also a box. Right here, if you want that.
Times -3. I got 1 over.
You only have to do the first 2 right now. You can go on if you want. That's what's on this side.
Wait. I've seen but it's a special 0, 0.
Who thinks they know the first one? The first one, yeah, what's the answer? 3, I see a 3. Anyone else? Let's just do that one real fast. If I plug in 0, I get 3 over 1, which is 3. Did something bad happen to me? No. So that is the answer. That is the limit. You plug in, nothing bad happens. That's the answer. Okay, I have a feeling something bad might happen for the second one. Yeah, it does. All right. And so then you're going to have to cancel, right? That's the only thing you know how to do is cancel. So if something bad happens for the second one, you're going to have to factor and cancel and then try to plug in again. I'll give you a second to do that and then I'll show you. All right, let me show you. You ready for the answer for the second one? Yeah, okay, here's the answer for the second one. So let me walk you through this, because it's the first time we've done one of these. First of all, if you try to plug in, so I just put the -3 in, and if I just stick the -3 in everywhere, I get 0 over 0, and I am stuck. Okay, it's fine to write that on your paper, right? In fact, it's great to write that. Write in where you're plugging it in. When you get 0 over 0, say, okay, that was not so good, so I'm gonna have to do some algebra. So what you do is you factor the bottom. Notice I factored the denominator here as x plus 3 and 3x minus 1. That's probably the hardest part of this problem, is just doing that factorization right. Once you do that, the x minus 3's cancel. And now when you plug in, you get -1/10, which is fine. And so that's the answer. I like to think that this extraneous factor of x plus 3 was like masking the real answer. Like if I multiplied -1 over 10 by 0 over 0, that'd be a problem, right? And that's exactly what was happening to us. So you plug in, something terrible happens, so you do some algebra, which in this case is factoring and canceling. Then you try plugging the limit in again, and you get a number, and that's the answer. Does anyone want to ask about that? By the way, our goal is to get good at calculating limits. Notice I don't need deltas and epsilons now, right? I'm not trying to find the largest delta or something. I can just straight up calculate what these limits are. And then in the next chapter, we'll use these limits to define this thing called derivatives, which is kind of the point of this semester, okay? So we're getting to be experts on limits. Okay, so next two. Give the next two a try. Now things are getting worse. Remember, try to plug in first and see what happens, at least for the first one.
Yeah, I got this. You need to.
I got it right to the end. What did you do? Find it out. Cancel that.
That's weird.
Negative. Yes, that is good. Yeah, I believe that I was right. I haven't completed that part yet. I was just being told. But I know what problem that is, what's it's supposed to be, so that should be correct. All right, who's got something to say about the first one? What should we do? Not what's the answer, but what should we do? Wait, before that, what should we do? Plug it in. What happens if you plug in 0? Bad. Why is it bad? What do you get? 0 over 0. So does everybody get that? The first thing, always plug in. Do you want to do algebra if you don't have to? I do not. Okay. If you plug in and nothing bad happens, you're fine. Okay, then you look through this and compare to what you have, and then I'll talk through it. So let me talk through this just for a second. The thing on the top is where you plug in and a bad thing happens to you. Okay, so that's what happens up here. Then I multiply it out at the top. Notice I'm still writing the limit here. You have to keep writing that because you didn't take the limit yet. After I multiply at the top, some stuff cancels. I get a new limit, and more stuff cancels. And notice I didn't try to plug in again after the first step, because you know you have to cancel a numerator and a denominator, right? Your problem is 0 over 0. So you definitely want to be canceling something that is 0 on the top at your point, divided by something that's 0 at the top at your point. So I'm not actually done until these h's cancel. And now I have a new limit. And the cancellation theorem for limits says that these two limits have the same answer, because all that happened is that I canceled. And this limit is easy to calculate. I plug in 0 and I get -2. Those of you that have seen calculus before, or those of you that want to see a glimpse of the future, this is the derivative of x squared at -1. Those of you that have had calculus, what's the derivative of x squared? 2x. Very easy. Okay, say it again. What's the derivative of x squared? 2x. People are just memorized that. Okay, so even if you haven't had calculus, now you've memorized that, whatever it means. 2 times x is 2 times -1, which is -2. Okay, so we'll have a much faster way to do this in chapter 2. Okay, the last one I want to go over with you, because when you have a piecewise function, the way to write this out correctly is to take the limit from the left and the limit from the right separately. You have to, because the limit as x goes to 0, that's right at this break point. So we have to look at the left and the right separately. From the left, I use the function that applies to the left of 0, and from the right, I use this second function because that's what applies to the right of 0. But once I've done this setup here, the rest of the problem is easy. I just plug in and nothing bad happens to me in this case. On this side, I get 1. On the other side, I get 1. Those match. So the limit is 1. Okay. This is sort of a more abstract version of the question that I asked you at the beginning of class, which is just kind of, does the function match up? Can you make it continuous? This is like actually justify what the limit has to be given the tools that we have. So piecewise, you'll have to look from the left and the right. That's the other wrinkle, I guess. Okay. I think that is it. I didn't look at these questions, so I don't know if there are any, but I'll just ask if you have any questions about this right here, or about anything to do with the class or retake week, anything that's coming. Any last minute questions? Yes. Oh, let me say that really fast. In next week, I will give you qualifiers for the retakes, which will basically be like quiz corrections and then answering a question. And then you'll have to hand those in, and that will make me make you a quiz, which then you will get in the 9th week. Okay. And I will always take the higher of the two. Certainly. Yeah. Yeah. Okay. That is all. I'll see you on Friday. Good luck, everybody.